This lecture is the first on geometry and will be concerned entirely with geometric representations. Geometric representations are natural generalizations of numerical representations. There are two reasons for the interest in geometric representations. The first is historical. Actually, the first representation theorems were proved in the framework of geometry rather than in the framework of measurement, in terms at least of modern mathematics. The one we all associate, the name we all associate is Descartes, and the proof of the equivalence of the analytic representation and the synthetic geometric representation of Euclidean geometry. The second and more important reason, going beyond the historical, is the use of multidimensional representations in many different parts of science. We perhaps will have time to discuss some of those applications. There will be some discussion in the second lecture and in other lectures in the course, but they will be familiar to many of you in different areas and applications. Now, the purpose of this lecture is not to cover in depth the enormous topic of geometric representations. The intention is to cover main topics that will be of use and provide a general orientation. The lecture is divided into 5 main parts. We'll begin with vector spaces, then discuss analytic affine geometry, then analytic projective geometry, then analytic Euclidean geometry, and, if time permits, a short discussion of the topic of meaningfulness in geometry. So let's now turn to the first topic of vector spaces. The concept of a vector space will be familiar with many of you, and what we want to do in this first part of the lecture is to review those familiar facts. We take it that we have already available the concept of a field. Now, in talking about fields, in most applications in science, we take the field to be the field of real numbers. Most of the definitions we give will generalize beyond that field, but in applications almost entirely will be restricted to the field of real numbers. So we'll go back and forth between an arbitrary field and the field of real numbers in discussing the various topics in front of us today. So let F be a field. The triple V, which is a set, and the two operations plus and multiplication constitute a vector space over F if and only if, first, the addition is a closed binary operation from V cross V to V, and multiplication is multiplication by a scalar. That is, it's a binary operation from F cross V into V. We then say that if the following axioms are satisfied, such a triple is a vector space. We require that there exist an element 0 in V, such that for every x, y, z in V and every t and u in F, the following are satisfied. And in axiom 1, we have the familiar properties that make the vector space a commutative group under addition. Namely, the operation of addition is associative, that's property 1. Secondly, it's commutative. Secondly, that we have an identity element, the 0 element. And fourth, that we have an inverse element for every x in V. An inverse, that is, with respect to addition. The second axiom are the familiar axioms governing scalars. The first property is that the multiplication of any sum x plus y of vectors by a scalar t is distributive. It's equal to tx plus ty, and correspondingly the distributive property of multiplication by an addition of two scalars t plus u times the quantity x is equal to tx plus ux. And then the associative sort of property 3 for scalars, the scalar tu times x is equal to t times the vector ux. And finally, fourth, 1 times x, that is the number 1 times x, is equal to x. Those properties will be familiar, represent the beautiful algebraic characterization of vector spaces. Familiar models of these axioms: first, we take the Cartesian product of the real numbers n times, and we define multiplication by multiplication of each component of the vector by a scalar, and addition of two vectors as coordinate-wise addition. That's a familiar model of an n-dimensional vector space over the real numbers. A second familiar example is again to take the field to be the set of real numbers, and now to take V, the set of vectors, to be the set of L times n matrices. And addition is familiar matrix addition, and multiplication is multiplication of every element of the matrix by a scalar. The first, and in many ways the most fundamental concept for vector spaces is that of linear independence. We say that vectors x1 to xm in the set V, that is vectors in the set V, are linearly independent if and only if the following condition is satisfied. For all scalars t1 to tm, when we multiply the scalars by the vectors in the manner indicated, t1 x1 plus out to tm xm, if that sum is equal to 0, then all the t sub i's must be equal to 0. And that is the condition in order for all of these vectors to be linearly independent. Now, we use the notion of linear independence to define dimension. The dimension of a vector space is n if and only if the vector space has n linearly independent vectors, and furthermore, if we take any m less than n linearly independent vectors, they can be enlarged to n such linear independent vectors. And, of course, finally, no n plus 1 vectors are linearly independent. The second condition, of course, is required in order for the dimension not to be greater than n. So that's the familiar and standard definition of the dimension of a vector space. In terms of these concepts, we can then formulate the basic representation theorem for such vector spaces. A vector space satisfying the axioms we have given has dimension n over F, its field, if and only if there is an isomorphism phi of the vector space onto the Cartesian product of Fn times with plus and times defined as already discussed, where phi is an isomorphism, and now this characterizes what we want to mean by saying that phi is an isomorphism, if and only if what? The following four conditions are satisfied. Phi is a mapping of V into the Cartesian product of Fn times. Secondly, in order to be an isomorphism and not just a homomorphism, phi is 1-to-1 and onto. And third, the structural properties are preserved, namely 3, phi of x plus y is equal to phi of x plus phi of y, and 4, phi of tx is equal to t times phi x. Notice that the way this is formulated, of course, we are using the same sign of addition for vector addition in the vector space and in the n-tuple representation. And we have a fixed field, so t is the same scalar both inside of phi and outside, so to speak, because we have a fixed f. That's what we mean by isomorphism, and we're saying now that we have such an isomorphism for a vector space of dimension n, and moreover, and this is the uniqueness part of the basic theorem, moreover, if we have two such phis, let's say phi and phi prime, that establish an isomorphism of the vector space into the n-dimensional characterization over the field, f super n, two such phis, phi and phi prime, establishing such an isomorphism, are related by an n by n matrix with determinant not equal to 0. So that's the basic representation and uniqueness theorem for such vector spaces. Now, a natural question is, to what extent can we generalize the apparatus we've introduced here? Well, there are two respects in which generalizations arise in a rather intuitive fashion. One is, and it's rather obvious from the way we have discussed Theorem 1, we could, of course, have two different base fields, f and f prime. So the isomorphism could also carry one field into an isomorphic field. But that generalization is not too useful to us because of the primary concentration on the field of real numbers. The second generalization is perhaps more important. There's a long history of considering vector spaces over weaker structures than fields. A good example would be vector spaces over division rings. Vector spaces over division rings generalize in the following way: that division rings are not necessarily commutative. And of course then we have to go back and be careful about the scalar multiplication from the left and from the right. The generalization over division rings is important especially because of a classical theorem about the projective plane that we will study in the second lecture. This classical theorem says that for projective planes satisfying Desargues' property but not Pappas', we can get a representation in terms of a two-dimensional vector space over a division ring. We want to take now what we said here about this general concept of vector space and turn to these particular special topics that I mentioned earlier, beginning with analytic and affine geometry, and then going on to analytic projective geometry, analytic Euclidean geometry. So we turn now to analytic affine geometry, closely connected with affine spaces, as we'll see in a moment. And in such geometry, or in affine spaces, lines are preserved and the parallelism of lines, as well, for example, as the parallelism of two planes. But we don't have preserved, as we do in Euclidean analytical geometry, congruence or perpendiculars. Such geometries, therefore, constitute a generalization of the familiar Euclidean case, but an important generalization that still has many applications. We assume for everything we say about analytic affine geometry that we have in the background a vector space satisfying the axioms we just discussed. The first thing we want to define is the notion of a linear variety, or as I'll sometimes say simply, a variety. Let x1 to xk be linearly independent elements or vectors of V. A k-dimensional linear variety, which I'll call cap A and put in brackets x0, x1, xk, is the set of all elements of V such that it is either the single element x0 in case k equals 0, or it's the set of all elements of V defined as follows: x0 plus the sum of the products t sub I xi, where t1 to tk are any scalars in F. Let's take a couple of examples of this, because this definition has very familiar instances. The linear variety for k equals 0, or we'll sometimes say of dimension 0, of course, are points. Linear varieties of dimension 1 are lines, characterized then by x0 plus tx1. Notice we didn't include in the linear independence any requirement on x0. It's the vectors multiplied by the scalars that we require linear independence of. So, of course, in the case of lines, we don't have any problem. In the case of k equal 2, that is, linear varieties of dimension 2, we get planes. In this case, x0 plus t1 x1 plus t2 x2, with the requirement now that x1, x2 be linearly independent vectors. The second thing we want to define, then, is the relation of incidence for linear varieties. First thing to note is that that relation of incidence is not the same as intersection. For example, the intersection of two lines is not a case of incidence. Incidence holds only between varieties of different dimensions. For example, we have incidence when a point is on a line, or a line passes through a plane. Or rather, a line lies on a plane. I've got this drawing slightly wrong. I want to change that. More like this. Let's look at the definition. A variety cap A is incident with 1b if what? A is in the set of varieties of dimension k. We'll write that script sub k. B is in the set of varieties of dimension L, where L is not equal to k. And secondly, either A is a subset of B or B is a subset of A. Notice in the case I have drawn here, of course the higher dimension is always the larger set here. The point is incident with the line, and of course the point is a subset of the line. In the case I've drawn here, I've sketched a plane, and the line that's incident with it is a subset of the plane. We are now in a position with the notion of variety and the notion of the relation of incidence added to our characterization of vector spaces to define what we mean by an n-dimensional analytic affine geometry over a field F. Such a geometry is just a structure V plus multiplication, where we have additional multiplication, and then the varieties of different dimensions, a sub 0, a sub n, and the incidence relation. So such a structure, where, as already said, V addition multiplication is a vector space over F. The variety is as defined, and the incidence relation is as defined. That's what we mean by a geometry. What is important about this concept of geometry from a broad set theoretical standpoint that takes us beyond the vector space is to include as particular structures within the vector space the different linear varieties of different dimensions, as well as their relation of incidence. We let now, to define the concept of an affinity, let script V be the union of all the varieties of different dimensions. So that's union of the a sub k's, k equals 0 to n. And an affinity C is defined as following. It's a mapping of V into V, and it preserves varieties, and it preserves incidence. When I say it preserves varieties, I mean more than that. Namely, it carries any k-dimensional variety into another k-dimensional variety. So if A is an a sub k, then C sub A is an a sub k, and that goes both ways. Secondly, if A and B are two varieties that are incident, then their images under C are incident. So we have AI, A incident B, if and only if CA incident CB. Now, in terms of what concepts we've introduced, we mentioned at the beginning some important affine concepts. Let's say something a little more about that. Another way of stating important concepts is to emphasize once again the concept of parallel holds in affine geometries. Secondly, the concept of intersection. intersection we can define set theoretically for varieties or any other figures. So, for example, meaningful is the intersection of two lines, a line on the plane, etc. And at least as important is the concept of span. We have the familiar idea of two distinct points spanning a line or determining a line. Three non-collinear points spanning a plane or determining a plane. So that notion of span is also an affine notion. When we say it's an affine notion, we mean that no stronger geometry is needed in order for that concept to be defined and to be meaningful. From the concepts that we have introduced, a natural question arises. Intuitively, in ordinary experience, if we think of mappings in geometry, an affinity is the natural kind of concept. That is, something that maps figures into figures, not transformations, mapping individual points into points. A natural question arises, what is the relation between affinities and transformations of the space itself, the space V? Well, there's a beautiful theorem that we won't prove here. In fact, we won't prove any theorems in this lecture because we're reviewing just the basic material for use later. But the beautiful and basic theorem is that the field F have no non-trivial automorphisms, for example, be the field of real numbers. Then we can characterize the affinities for affine analytical geometries over F in terms of automorphisms, alpha of the vector space plus a possible translation. In particular, we can show that there exists an alpha, that is an automorphism alpha, and a vector y0 such that for every variety A, C sub A is equal alpha x plus y0, where x is a point, a vector in A. So that gives us a beautiful characterization of an affinity C just in terms of such an automorphism and such a possible translation. Now, there's just one other remark to make about affine geometry that's important for the second lecture. When we do affine geometry synthetically, starting from qualitative notions, the most important concept is the notion of order, which we haven't mentioned here. And that is the order in terms of betweenness. But it is easy to add the concept of betweenness in analytical geometry in the standard fashion. This is just the relation of betweenness that holds along any line in the affine geometry. And we then can obtain a representation for the synthetic geometry in terms of such ordered analytical affine geometries over a field once that relation of betweenness is added. I won't write down the details. I think they're obvious. We now turn to analytic projective geometry. The basic idea is to identify any two non-zero vectors which are proportional. In particular, we have that a projective point is equal in terms of our basic vector space as the set of all vectors Tx, where T is in the field and T is not equal to 0. Projective line is then a set of projective points obtained from two distinct projective points by linear operations. In such an identification, we lose one degree of freedom so that an n-dimensional projective geometry is obtained from an n plus 1 dimensional vector space. In the next lecture, we shall go back over these very same basic ideas from a qualitative standpoint. Here we want to continue and define, in exact parallel to what we did for affine geometries, first the notion of a projective linear variety. Such a variety L, determined by x0, xk vectors, which are required to be linear independent, is the set of all vectors obtained from the summation t sub I, x sub I, where the scalars t sub 0 to t sub k, are in the field. definition, as you'll note, is very similar to what we had for the affine case. L sub k is in the set of all k-dimensional projective varieties, and P for projective is the set of all varieties taken over all dimensions. Next, as in the case of the affine geometry, we define incidence in exactly the same way, so we won't repeat that definition. We then say that a structure, V, addition, multiplication, varieties L sub 0 to L sub n, incident, such a structure is an n-dimensional analytic projective geometry. Notice that it corresponds to just what we did in the case of the affine case, except now we have the new definitions of varieties for the projective case. We have a corresponding new definition of a projectivity corresponding to an affinity. A projectivity C is a mapping from the set of all varieties P into itself, preserving the dimensionality of each variety, and it's being a variety, of course. That is, L is in the set of k-dimensional varieties, if and only if C of L is also in that set. And secondly, preserving incidence. L intersects M if and only if CL intersects CM. And again, we have the same natural question. Projectivities are mappings of varieties. How can we relate that to automorphisms that map points? And again, we have a very similar fundamental theorem that may be regarded as the fundamental theorem of analytic projective geometry. Namely, a mapping of P into P, that is a set of projective varieties into itself, C, is a projectivity if and only if there exists an automorphism alpha of V such that C sub L for any variety L is simply the set of points alpha x where x is in L. Notice this is a simpler form because of passing through the origin in the case of the projectivities than in the case of the affinities. Again, we have the restriction here that I haven't written down, that the underlying field should have no non-trivial automorphisms. We can take, as always, the reals as such a field. There is a point now about the relation between an analytic projective geometry and its representation over the appropriate Cartesian product of the reals that needs to be mentioned because of the standard use of homogeneous coordinates. It'll be sufficient here to consider the case of the representation of the projective plane over the field of reals. The representation is then in terms of the triples of reals, with the vector space being triples of reals, with the addition of vectors and the multiplication by a scalar being defined in the usual ways, and with projective varieties L sub 0 points, L sub 1 lines, and L sub 2 planes, and the relation of incidence. And a point in this coordinate representation now of homogeneous coordinates, a point in L sub 0 has homogeneous coordinates where x is some vector x1, x2, x3, not identically the origin 0, 0, 0. It's a set of all points tx1, tx2, tx3 where x is not equal, where t is not equal to 0, just as we discussed before. Notice that we're in the plane, but we have 3 coordinates, and that's because we have this homogeneous representation. A line, a projective line in L1 then is represented in the following fashion. We consider T0 scalars T0, T1, not for the pair is not identically 0, 0. And then the three coordinates are t0, x0 plus t1, x1. That is, we have given two vectors, x0, x1, that are linearly independent, and now we're considering them coordinate-wise. So we have the similar thing for the second coordinate and the similar thing for the third coordinate. What's written down here is more complicated in appearance than it actually is. And again, the important point is that though we're in the projective plane, because of the homogeneous coordinates, we have three coordinates. We don't have the time here to study in a detailed way the way in which homogeneous coordinates are used. We'll be able to say something more about them in the second lecture, but mainly we'll just have to emphasize they are the standard form of representation for projective geometry. Now, there is an important duality fact about the projective plane, for example, that I want to mention. That 2 points uniquely determine a line, that is, 2 distinct points uniquely determine a line, which we would expect from the Euclidean case, but also always 2 distinct lines uniquely determine a point. Notice, of course, in the Euclidean case, this is not true when the lines are parallel, but it is always true in the projective case. And consequently, we can interchange by symmetry. We can see that much easier in the case of the synthetic axioms we'll consider in the next lecture. We can always interchange propositions about points and lines to get a new proposition where the role of lines and of points and lines is interchanged. Now, the point that I haven't mentioned that is important in all of our considerations in the theory of measurement, what about the problem of order in the case of projective plane, for example, or projective space of arbitrary dimension? There is an important concept of order, which we call separation, and it's a 4-place ordering relation. Notice how, as we go to these geometrical cases, we continue to have to generalize and make somewhat more complicated the concept of order. When we're just dealing with the real numbers, then we just have the ordinary binary relation of ordering. In the affine case, we go to the relation of betweenness. That's also the ordering relation that we have in the Euclidean case. But in the projective case, we need something more complicated because betweenness is not preserved under projectivities. In the second lecture, we'll talk about the qualitative properties of separation because it's an interesting ordering relation. Here, I just want to say something about its intuitive meaning. What we say intuitively is that the points A, B separate the point C, D, and conversely. And that relation of separation can be seen by drawing the points on a circle. Notice, of course, that betweenness is not well defined on a circle. So AB separates C and D. That is, if we tried to pass from C to D, we must encounter either way we go, either A or B. And correspondingly, if we try to go on the circle from A to B, either way we go on the circle, we must encounter either C or D. And so we say that AB separates CD and CD separates AB. And this notion of separation is the notion that is preserved under any projectivity. So if we have, for example, a line, the order looks like this. We'd have AB, CD, and that kind of separation under any projective projectivity or under any appropriate automorphism is preserved. We'll have more to say about that, but it's an interesting and important case of ordering. We next turn to analytic Euclidean geometry. Intuitively, we can think of getting Euclidean geometry by introducing in affine geometry the concept of perpendicularity. Formally, we define a Euclidean scalar product, and we'll show how it's related to the qualitative concept of perpendicularity of two vectors. Such a scalar product is a mapping from the Cartesian product of the vector space with itself into the real numbers. Here we'll restrict ourselves just to the underlying field being the real numbers. And such a scalar product must satisfy three basic axioms or properties. First, bilinearity. The product of x plus y with z must equal the product of x and z plus the product of y and z, and correspondingly the product of x with the sum y plus z must equal the product of x and y plus the product of x and z. And in the case of scalars, the scalar product of tx with a vector y must equal t times the product xy, which is itself equal to x times the product ty. In the last case, the scalar product of x with the vector ty. The symmetry is, as to be expected, the scalar product of xy is identical to the scalar product of yx. And the important property, finally, of the scalar product being positive definite, if a vector is not equal to the zero vector, then the scalar product of x with itself must be unequal to not be equal to the real number 0. What we can then show is that where we have a vector space over the real numbers and we introduce this concept of Euclidean scalar product, that x is perpendicular to y if and only if the scalar product of x and y is 0. That is, what we can show is that that defined concept of perpendicularity has the expected Euclidean geometric properties. There are several other familiar Euclidean notions we introduce using the notion of scalar product. First is the notion of the Euclidean norm. We use the double vertical bar. So the Euclidean norm of a vector x is equal to the positive, that is the non-negative square root of the scalar product of x with itself. We can then use the norm to introduce the standard Euclidean metric. The distance between x and y is, as points in the Euclidean space, is equal to the norm of x minus y, which is equal to the square root of the scalar product of x minus y with itself. We also have defined then in terms of the metric the standard concept of congruence for line segments. xy is congruent to x prime y prime if and only if dxy, that is the distance between x and y, is identical to the distance between x prime and y prime. We might note that in other spaces, for example, the Minkowski geometries, which we also discuss in the general treatment of geometric representations, but don't have the time to cover in this lecture, the norm is there, but it doesn't come in a direct way from a scalar product, and that differentiates, in one sense, the Minkowski geometries from the Euclidean ones. The next point is that in analytic Euclidean geometry, we introduce order in the same way that we do in the affine spaces. As you might gather from this, the analytic Euclidean geometry is closer to affine geometry than it is to projective geometry. Because this is seen in the order relation. The order relation in the Euclidean case is just between this, which we already considered in the affine case. Now we want to establish some of the standard relations between mappings, some of which you'll know from other contexts in which you've learned about Euclidean geometry. Let this structure, V, addition, multiplication, A sub 0, A sub n, incidence relation and ordering relation between this, be an n-dimensional ordered affine analytic geometry. And let us have an addition, the standard Euclidean scalar product defined in the vector space, satisfying the axioms just given. We also assume we have the norm as defined, the Euclidean distance, and the congruence and perpendicularity relations. We then say, using all of these concepts, that an affinity C That is an affinity now in the sense of the analytic affine geometry. An affinity C is a similarity, similarity being a Euclidean notion, is a similarity if and only if either one of the following properties hold. These two are equivalent. The first is that if we take two vectors x and y in V, C sub x minus C sub 0 is perpendicular to C sub y minus C sub 0 if and only if x is perpendicular to y. So we use in condition 1 perpendicularity, the preservation of perpendicularity, to characterize similarity. And in condition 2 we just use preservation of congruence. Cx cy is congruent to Cx prime y prime if and only if xy is congruent to x prime y prime. What this shows is that this equivalence and many other results that can be proved is that we can take either perpendicularity or congruence of line segments as the notion we add to go from the affine to the Euclidean case. It's probably more common to take congruence, but one can take perpendicularity as well. In our discussion of the synthetic case, we will axiomatize Euclidean geometry from the affine case. The affine case takes betweenness as the basic notion, and will add to that this notion of congruence qualitatively. But we could have taken perpendicularity. The second concept we want to define is that a mapping of the vector space into itself, a mapping C, not necessarily an affinity, a mapping C is a motion if and only if it's distance preserving. That is, one way of putting it, Cx Cy is congruent to xy. That's a familiar and concept, corresponds exactly to the familiar concept of motion in Euclidean geometry. And third, we say that C is an orthogonality if and only if the scalar product is preserved. That is, the scalar product of Cx Cy is identical to the scalar product of x and y. And then we have, as a basic theorem relating these concepts of similarities, motions, and orthogonalities, the following. First, every motion is a similarity. Notice, of course, we would expect that, but the other part is interesting too. Every similarity has the form alpha c, where alpha is simply a fixed real number, positive real number, and c is a motion. So that a way of thinking about similarities, the standard way, is to say, well, we have a motion, and then we have the possibility of a stretch, where alpha represents the change in the unit of measurement. Third property we have is that every orthogonality is a motion, and every motion has the form c plus x, where x is a vector, a point in the space, and c is an orthogonality. Notice what this says is, well, let's look at 4 and then come back on that. 4 says that when we look at the standard n-dimensional Cartesian representation, REN, then orthogonalities are represented by orthogonal matrices of dimension n times n. Now, such matrices, of course, are just a way of representing rotations. So intuitively speaking, what we have is that we have orthogonalities or rotations. Motions are rotations plus possible translations. Similarities are motions plus changes in scale, or another way of putting it, similarities are possible rotations plus translations plus changes in scale. And these are the familiar possibilities of transformations in Euclidean geometry. Note, of course, that similarity does not preserve congruence. Motions, and of course orthogonalities as special cases of motions, do preserve congruence. From a basic geometric standpoint, it's similarity that is important. But for many different reasons historically, congruence is often given precedence, which means that the unit of measure must be fixed, and we exclude similarities that bring in a unit of measurement. But when we look at the qualitative axioms, the actual representation that one gives is natural to give only up to a similarity, and not up to something, not up to a motion. As I said at the beginning of the lecture, the intent is to end this lecture with a brief discussion of meaningfulness in analytic geometry. What can be said here is necessarily rather superficial. It is meant to supplement in a very brief way the general lecture on meaningfulness. There is a long historical tradition, however, that I would want you to be aware of, and that is the historical relation between identifying a geometry and its group of permissible transformations. The study of such uniqueness properties in terms of the group of transformations historically precedes similar discussions in the theory of measurement. Perhaps the most famous statement of such a characterization of geometry in terms of the group of permissible transformations was due to the famous German mathematician Felix Klein in a lecture he gave at Erlangen, Germany in 1872, in which he went so far to say that geometrical properties and a geometry are defined or characterized by the widest group of transformations under which they are invariant. So, for example, it's possible to study axiomatizations of geometry in which we use this invariance under motions, for example, in the Euclidean case, or transformations more generally, affine transformations in the affine case, etc., to actually characterize the geometry. It gives a set of axioms that are very simple and rather different in spirit from the kind of qualitative axioms using intrinsic geometrical relations that we shall consider in the next lecture. Now, of course, the synthetic program we'll talk about next time can be regarded as the converse of Klein's program. Namely, we characterize the group by giving geometrical properties and the axioms they satisfy. Thus, for example, we characterize the group of similarities by the qualitative axioms for Euclidean geometry in terms of the two geometric concepts of betweenness for order and congruence for line segments, as discussed just a few moments ago. In the case of affine geometry, we can characterize the group of affine transformations just in terms of the qualitative relation of order, namely the relation of betweenness. In the same way, as we'll see in the next lecture, we can characterize in similar fashion the projective transformations in terms of relations such as those of incidence. It's important to recognize that the uncovering of this relation in the 19th century in an explicit way between geometric properties, a particular geometry, and the permissible group of transformations leaving properties and relations invariant was a major discovery and gave a way of looking at geometry that has been important ever since. That way of looking at geometry in terms of transformations goes over into measurement in terms of the discussion of different kinds of scales, and this way of thinking about geometry reflected into problems of measurement really constitutes the major focus of the general topic of meaningfulness, which constitutes an independent lecture in this series.